So what do we want to go over for the final? If I recall correctly, we already talked about size and the format and all that fun stuff. Right? Not just limited to the materials and the practice tests, all semester long. True, false. Sometimes those are actually harder than one would think, because the answer to your CS41 is data structures would be false, because there are explicit cases where there are classes that are not CS41 that are something else, and there are other data structure classes that are labeled differently depending on where you are. So yeah, that's a strategy when approaching true false questions. Can I make this statement false with an example? If the answer is yes, then typically that's how it should be on the key. Be right back. 1 second. $68 points. Yeah, there'll probably be about 50 to 68 questions. Yeah, whiteboards are available. Right, the final is big. Do not rely on trying to figure things out on the fly. You either know the question or you don't. If you don't, skip it. Save it for later, come back. Because there's definitely a time pressure on the final exam. Two hours and 10 minutes. AVL trees. All right, so we'll have two possible rotations. We have an insert to the right, or to the left, and it will be a single rotation. All right, so we do like a 21, 42, and then something that is greater than 42. We'll get balance here. 21 reporting as alpha. 42 is beta. 42 pulls itself up. 21 becomes a child. And we're balanced again. Interesting. All right, so there's the mirror of that. Then we'll have multiple rotations depending on where things go. All right, so both of these additions do not cause any imbalance in the tree. But if we go ahead and add anything to 44 subtree. And subtree has 2 nodes into it. 2 nodes is all you can do. 4 nodes. 4 nodes is good as long as the first 2 levels are complete. And then when we get back up here to 42, not gonna like that. Then we have 1 level on the left and 3 levels on the right. We insert it into the right subtree of alpha and its left subchild of beta. So we're going to do a double rotation. So 44 is going to be the one that's got a lot of legwork to do. 44. Let's see. All right, we're doing a lot of moving. So 44. We'll move up. Since there's no right subtree on 44, nothing has fallen off at the moment. Makes the first rotation less problematic. And then it has to rotate again. So alpha slides down. 44 slides up. This time we are going to have 43 fall off. All right, 43's ancestry 4. Right, right side we had 44, left side we had 42. We'll have the same thing here. Right side we're drawing vertical lines down through the tree. 43 we'll have 44 to the right and 42 to the left. All right, it's by search tree. We can just see the values. 43 needs to fit anyways, but the relative position is going to be the same as it was before, right? So 43 fell off, right parent, immediate right parent 44, immediate left parent 42, and immediate left parent 42, immediate right parent 44. Right, that holds the same. Okay. What is the unit distribution like for equations on the final? All right, so it's, about 15 to 20% test 1, 15 to 20% test 2 through test 5. And then they're like 10% be like the section 6 stuff, 10, 15%. And there wasn't as much material in section 6, so there's not that many questions on the final. As much as the final as possible will be like today's test, so I can auto grade it. But it doesn't restrict us from free answer questions, right? Some free answer questions can still be auto graded. All right, what's the next question? The distribution is intended to be more or less even across the semester. Go over unit 4 in general. You have to be more specific. Which part of graphs do you want to talk about? Grade. These specific questions. We got our redundant array, inexpensive disks. The important thing here is not priority queue, parity bit. is in use on some of the RAID schemes. All right, you don't need to memorize what 0 is, 1 is, 5 is, 6 is. It doesn't matter. We're simply talking about RAID because it is a very often used strategy in computer systems out there, especially in server farms and all areas of space that is using parity bit. So parity bit is the important part for that. Bipartite graph and a complete bipartite graph. Okay. All right, so for bipartite, just means we have two sets. No edges within a set. And so create a set of vertices in each set. Doesn't much matter what the labels are, how many there are in either set. The key thing is the edges, no edges exist within set A, M, X, whatever you want to call it, set. And same thing with this other set, no edges exist within. Now, if we wanted to make this complete bipartite, complete is fully connected across two sets. All right, so we have two vertices in this set. That means we should have two edges for every vertex in the opposite set, and then the converse will be true. Get my lines at the same points here. Get my lines more or less close enough. All right, so the degree of every vertex in one set is equal to the number of vertices in the opposite set because that's the one that's connecting to. All right, so you can figure out that there are no real patterns in with just a bipartite graph. Right, cycle graphs are bipartite when they have an even number because it's skipping. Right, you just redraw it. Uh, wheel graphs are complete bipartite, and because they're cross-listed, right? So we have just if I get rid of one of the vertices in the center right here, it just becomes a wheel graph. Sorry, a star graph. Wheel graph's not going to fit in a bipartite situation at all because there's just too much connectivity going on there. How do you know how to classify shapes, characteristics? Right, so the various shapes have patterns associated with them. Cycle graphs, everyone has a degree of 2. So if you see everyone has a degree of 2, it's very much probably a cycle graph. Right, star graph, everyone has a degree of 1 except for that central vertex. Wheel graph, it's the same thing. Central vertex connecting all out, and then everyone else has a 3 for their degree. Complete, pretty much everything's filled in except the diagonal. Cycle, star, wheel, complete, bipartite, unless it's complete bipartite, there's no pattern. The complete bipartite, you'll see rows are filled up within a certain subset of the range in the repeated pattern. All right, if we were to look at bipartite over there, we have 6 vertices of unknown names. But we'll just say we have set A1, A2, A3, A4, B1, B2. All right, A1's connecting to all of the B2 nodes. So we're going to have a pattern like this. Right, A is connecting to B's and only B's, and there's no cross connectivity here in the A to A range. So Dijkstra-Prim-Kresgel's algorithm, so Prim and Kreskel would be, spanning tree. Dijkstra is a single point shortest path. So which of those? Let's see, a follow-up question. Mention star graph is bipartite. Yeah, it's complete bipartite because you have a set with one vertex, the central vertex, and it's fully connected to every other vertex. So if we're trying to see if a just random graph is bipartite, right, we just draw it out. So start drawing. All right, just make a dividing line. Just start dropping some shapes, right? Drop some vertices, and first two that are connected, set them up, and then you can see who else this is connected to. So if it's connected to another vertex over on this side here, you just connect it up and you just try to look for somewhere where you can make it fail. Right, so if you can see if there's an edge between these two vertices, because it's just like a cycle graph, right, C3, and we know that this is failing the test because this line there, that line there is not allowed. But if we were to take this, make it a C4, that vertex wouldn't connect there. Connect to another vertex, which we can toss in the other set. And as long as this vertex doesn't connect to anyone already there, then we're good to go. And it bounces over there for its other connection. That's a cycle graph. Well, the sets are just arbitrarily, we're just split. We're trying to see if we can split uh, divide the vertices into two teams, right? And the teams are not necessarily being divided evenly, they're just being divided based off of relative relationships to each other. You start at any vertex, you just assign it to either set. It doesn't matter which set it's in. The labeling for set A and B is arbitrary. So it just goes into any set. And then you can try to add, just start adding edges. Yep. Just keep adding it. Try to dividing it into two sets until you see a rule violation, at which point it does not qualify as being bipartite. All right, so Prim and Kruskull's minimum spanning tree. Do I grab a tree here? That's a tree. Let's go grab that tree. Okay. Do, 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 do. Add a little space here so I can get some numbers. All right, good enough. Numbers, numbers, numbers. Right? If they were all one, just be a matter of cycle detection. At that point, we would definitely need to know what the vertices labels are, but go ahead and make this distinct set of edges based off of the weights. I have a 4 in there yet, and a 6. Okay, so that'll be our starting point. And we'll go ahead and do prim. Starting arbitrarily somewhere. It doesn't matter which vertex we add. To start off with, because every vertex will be added to the minimum spanning tree at some point. All right, and we have 2 edges to choose from. Let's see. Mm, Who needs margins? They just get in the way. All right, fine. Okay, so we've processed the vertex, looked at all the edges that it has to see what neighbors we have access to, right? So we can get to this node over here for 7. We can get to this node over here for 4. 4 is closer. So we'll bring that in. And we need to go ahead and look at the edges of that node. We have not already seen. And we have more options for neighbors. All right, so this particular edge, this edge is inside the spanning tree at this point, and the green edges are the potential edges that we could choose. All right, so we have a 9, a 5, a 7, and a 6. Prim's greedy, so it's going to choose the one that's closest that isn't already in the graph. And that will tell us about a new edge here. And this one edge will be a better way to add this vertex to the graph than this old 7 edge. So we'll go ahead and discard that 7 edge information. All right, so we can update the table. Say I don't like getting from that's central vertex to the upper right vertex. Instead, we'll get from there from the top vertex because that is much closer. All right, so we're bringing this one in next. Only one away. This new edge to look at, which will then cause this edge to be discarded. Because 2 is a much better way than 6. Oh, I forgot an edge there. Got this 3 edge. This 9 edge to disappear on us. And this one was the one. Have to add some colors in here. That's brought in. That's been brought in. We go update previous. All right. All right, so we still have 2 vertices, not in the graph yet. We have 2 edges at this point in time that are up for consideration, right? These dotted edges have been killed as possible paths because we have better paths. So between 2 and 3, 2 wins. No additional edge information. This vertex that's being added in there. So go ahead and grab the only edge remaining. And those yellow lines are our minimum spanning tree. Using prim. This shrunk down. Using the real estate. Okay. Now, Cruskle. All right, Cruskle's going to sort. So the first edge will process. Will be our 1 edge. As long as a cycle isn't created, we'll leave that edge in there. And we'll go ahead and grab a 2 edge. No cycle. No edge to remove. See if we get any cycles or not. In this one, 3's up next. Let's see. More than 5. And we'll be connected, so no cycles will be created in this particular example. All right, 4 edges added. Note that the spanning tree is a forest at this point in time. Just waiting for 1 edge to be added in such a way it doesn't create a cycle, and 5 is up next. And that's not creating cycles. There were many cycles in this example to start. But that is our minimum spanning tree. Redrawing a little bit so we're not overlapping things as much. Might as well get rid of the edge is not involved. I killed the wrong number there. Let's try and get back. Okay, that 9 went away, that 7 went away. That 3 was this edge. Okay. Match up over here as well. All right, and we have the same connectivity, same graph. Remember, it doesn't matter how we draw the graph. Right, if we want to bend this edge over here, still the same graph. This vertex is connected to this vertex sort of thing. Since it's a distinct minimum spanning tree, both algorithms will get us to the same answer. So what was the question for Dijkstra's single point shortest path? Or what's the next question? Or sorry, someone want to go over Hamming code. All right, Hamming code. Hamming code uses parity bits. Parity bits are used in such a way the data bits are covered by multiple parity bits. All right. First parity bit covers every other field. Second parity bit covers 2, skips 2, and repeat. Third parity does blocks of 4, and so on. All right, so if I were to ask a question here, let's see. Uh, Something along the lines of my positions are probably all wrong here. I'll have to go look that up. Maybe something along these lines where if the data is 1011, something like that, question B, are these parity bits correct for these given data bits type thing? So I would give you the table, give you the actual positions for where these things are, and then we can confirm which parity bits are correct or incorrect type thing. All right, next question. Yeah, we'll go over the test 5 later tonight once we're done with the final review. So final review, let's see. Practice test. We did this last week, but I'll do it again just to make sure. All right, how many runs? So we got 1, 2, 3, 4 runs needed for that one. Huffman code, what's code word for B? All right, so we got our fun tree building here. So we have D at 19. And we got C 25. E, that's fun looking E. 29. B 37. And then A 45. All right, so we'll connect these two together. Make 44. These two will get connected together to make a 66. And our 44 and 45 combine together. Make an 89. Then our 66 will attach next to that. Combine that together. So 66 was E, B, and all I care about is B for this question. So we had a 0, 1. Okay, next question. Decode this. All right, so you just keep looking at the table where you can draw the tree. Drawing the tree. Probably make things a little bit easier. All right. 0 left, 1 right. The one's a 0, 1. And do again 0, 1, 0, 1. 0, 0 is A, 0, 1 is B. 1, 0, 0 is going to be C, so this needs a branch. C, D, and E. All right, so we read a 0, so we go left. Read a 1, go right, so we got a B. And we reset. So grab my eraser here, erase, oh, too much, too much. Yeah, because zeros are left branches and ones are right branches. So when we're establishing what the code word is, once we figure out where B is in the tree, 0 left, 1 right. What week was Huffman codes from? Huffman code 6/2, November 27th. So just after Thanksgiving. All right, so we've got wrong tab here. Wrong tab. Here we are. All right, so 0, 1 was a B. So now we have a 1, 1, 1, 1, 1, 1 gives me an E. E, so it's a 1, 1. So we got 0, 0. So that's A. We got 1, 0. And it's followed by a 1. So that's D. So we got a B there. Compression rates. We've got 1,000. That's 500 divided by 1,000, which 0.550 should also work there. The key parity bit for that be 0 because that's 8 on bits. Bit repetition 3. I need to reword this question here. Oh, no, I didn't. I said bit repetition, right? So we're repeating the bits. So 1 is triple one. 0 would be triple zero. So that's matching so far. 1, triple one. All right, so what this should have encoded as triple one, triple zero, triple one, triple zero to match ours 1, 0, 1, 0. So if we decode this, this should decode 1, 0, 0, 0. So that doesn't work. So it decodes as 1, 0, 1, 1. So that one doesn't work. This one is 1, 0, 1, 0. So this one, even though there are errors in the bits, right? We got a bit corrupted there. We got a bit corrupted there. We got a bit corrupted there. We're still able to decode the correct message. Uh, let's see. Oh, apparently I did want that as a whole number. I have to make sure I update the key so that I can handle both. Let's see. All right, what's the next question? What's the point of the total? Right. Huffman code is how we're creating code words for data so that we can compress the unencoded text into encoded text that has a smaller footprint than the unencoded text. Totals, if you're referring to the notes, would have been how many bits of payload would be required to encode all of those particular items. Yeah, the count is the frequency of a symbol occurring in the data set, and we're using the frequency to dynamically determine the code words for that specific data set. All right, what's our next question? quick rundown of how quicksort works again. Ah, yes, now we're going back in time. All right, so assuming the lazy pivot approach, we'll have 28 as the pivot. Now we're trying to build our two sets. Values that are less than pivot, stay in left set. Values that are greater than pivot, go in the right set. And so immediately we have 41 in the wrong place. 82 is good where it is. 47 is good. 14 is not good. All right, so what we're going to go ahead and do is we will swap 14 and 41 to get our sets building up correctly here. So we can now keep building up. 17 is good where it is. 35 is not. Jump back over to the right side. We go over here to 12. And that is not in a good place. So we have values are in swap, 12 and 35. Swap, and we can continue. 4 is in a good place. 89 from the left's perspective is not in a good place. 89 from the right's perspective is in a good place. And then the left and right, we're going to get here. Left is here, right's here. Right says, I found someone out of place. All right, so we have the 4 values identified that are less than the pivot. So we'll go ahead and swap the pivot to its final sort of position at that crossover. All right, so all the values to the right, greater than. All right, so everything down here is less than the pivot. And everything here is greater than pivot. This is sorted. And that was one pass. Now we can repeat the exact same thing on smaller arrays. All right, the practice test for the final only covers the new stuff, which parity, encoding, memory compression stuff. What else? All right, memory compression, parity bits. All right, in Queens, it's just we haven't cover that in section 6. Not really particular to section 6. Let's see. There was a specific graph data structures that was V cubed. Yeah, that's the Floyd Warshall's all pair shortest path. Merge sort. Merge sort. A little bit of a similar idea here. So I can add a note here that this is quick sort. Merge sort. All right, so we'll divide in half. So we have 11 items here. So 6 will go one way. Split it in half. Split it in half. Split it in half. Now we have 2 one-element arrays, which can get merged together. We have a 2-element array with a one-element array. Merge those together. And we can go back to that splitting over here. Split again. And then get 2 one-element lists. We can merge together. 2-element list and a 1-element list. We can merge those together. And then we have our 2 3-element lists. They can be merged together. And so we got 4 versus 17, 17 versus 35, 28 versus 35, 35 versus 41, 41 versus 89, and then 89. And then we'll do these other 5. Same story, split. Keep on splitting until they are sorted lists. Once they're sorted lists, they can be merged together. And it's a sorted list. Then we gotta get to the splitting. 2 elements, merge them together. And then 12 versus 47, 14 versus 47, 47 versus 64, 64 versus 82, 82 left over, and then merge the two together. Or 12, 14, 17, 28, 35, 41, 47, 64, 82, 89. On my 4.9 notes, can you explain Kruskal's algorithm why FK7 and BC8 are not used? Because once you have a minimum spanning tree with Kruskal, any edge that you're going to process at that point is guaranteed to make a cycle, because you can only, any edge that is unadded at this point is going to be between a pair of vertices that are in the graph, rather in the tree from the graph, because we already have a tree at that point. And because Kruskal sorts, there is no improved information that we're going to get. Those weights are going to be greater than or equal to any edge that would be in the cycle that would be formed. It would be the edge that is removed. So it's, you're putting the plate on the stack and then you're taking it back off the stack. Put the plate on the stack, take it off the stack. There's guaranteed no benefit. So there's no reason to keep going. So the algorithm will stop. All right, did I miss a question? What else do we have? All right, so pivot selection, we have three strategies. The lazy approach, use the first index. Then we have just use the median index. Then we have the median of 3, which is use the median of the first, middle, and last value from the sets of data. Then choose the median of those 3 values, which could be the first, middle, or last values from that set of data. So if the last value is the median, then that value would be used. What do you mean sometimes we have a third one? There's there's always one pivot selected for any given partitioning pass. Explain how all sorts deal with arrays, odd numbers, let's just integer math. Left boundary plus right boundary divided by 2. Truncate the result. All right, so when we did this one, we had 0 plus 10 divided by 2 gives us 5. So this is our range to work with. And add 0 plus 5, right? 0 plus 5 divided by 2 gives me 2. That was our range to work with. Yeah, so the median, right, so when we're doing our pivot selection, let's grab a table here. First, middle, last. All right, so median of the first, middle, and last values. So if first is 3, let's do this. First, middle, last. First, middle, last, median. All right, 10, 20, 30, the median's 20. 10, 30, 20, the median's still 20. 30, 20, 10, median is still 20, right? The same three values. Doesn't matter where they are. In the table, the median is the same. 20. Fun permutations, right? 6 possible arrangements of those three values. The three values are the same each time, so it doesn't matter where they are. From that selection, the median of those three values is always the same. And that will be used as our pivot. The idea being the more medial a pivot value is, the better the left and right side ratio are going to be towards each other. Well, all three of these are possible pivots. If we're talking about what using all three methods, what are possible pivots, then it's 10 and 20. And if these are the arrangements of the numbers, then it's 10, 30, and 20. So the arrangements of the numbers would affect the answer to the question, which of these could be pivots using any of the three selection methods? Yes. So if these were the numbers in that question, then 10, 20 would be the answer. 10, 20, and 30 would be the answer. Right here would be 30 and 20. Here would be all three. And basically, whenever the median ends up in the third slot here, then it's all three. Otherwise, it's just the first two. What if the median is not a num on the table? Well, the median is a value from the array. Right? It's not the means. There's no precision lost. Median. Right? Median being the middlemost value. All right, what's our next question? All right, it's been an hour review. Let's go ahead and take a 5-minute break, see if there's any additional questions that pop up. And why is index 3 selected as median? Right, because 7 divided by 2 is 3 when you throw away the remainder. Now we're cutting the index in half. Yeah, let's take 5 and we'll be back. Let's see. On the syllabus, saw a couple of grading simulations. One, drop the lowest test score. Yes. And the extra credit applies to that test score. So that was dropped. Yes, it's possible an 89.9 could be an A. It could also be a B. It just depends. When will program 4 be graded? Probably after the final. uh, Graded 1 or 200 items in the last week or two, and I'm still in the neighborhood of 300 items to grade with test 5 between this class and the other class. There's another 100 items. Well, this test should be auto graded. No, I have to go in and add 1 point or however many points that shift folding question was, and cover that in the notes. So there's quite the long line of things. Program 4 is bigger programs. It takes more time to run that. There have been studies about with judges and the type of sentences they hand out based on the time of the day, before lunch, after lunch, other external factors. Definitely, there's definitely unconscious bias in the way that people do things. That's retrograde, one question at a time. Keeps things as consistent as I can make it. All right, I don't see any other questions at the moment, so let's go over test 5. You don't need to worry about the optimization for the test. Okay, test 5 should show you details at this point. Yeah, you don't have to worry about cranking down to the bits for the run length encoding. It'll just be an 8-byte int and an 8-byte symbol, 8-byte, 8-bit, 8-bit and 8-bit. Okay, collision, hash table, right? It's two values that to be normalized, try to go to the same index. So these definitely need to be different outside the range. No, normalize, same index. There we are. Garbage time. Yeah, we've got object C being tracked by X. No trash just yet. Now X and Y are tracking C. Z comes along here. Z is equal to X, which means B goes away. And then Y is equal to X, which it already is, so C is never reclaimed. Linked list typically has data fragmentation. I guess that's where we have got node A over here in memory. Then I got other stuff. And then I got node B here in memory. More other stuff. C here. All right, so physical space between these. External fragmentation does not apply. One can try to argue internal fragmentation, but that's a bit of a stretch. Let's see. Minimal perfect hash, which apparently is one of our duplicates. All right, it's perfect. So that's all the only part that matters. Makes a big O one. Minimal. That's just icing on the cake. Temporal locality reference. Recently used resource. Again in the near future. Yes. It's all time based. Math, math, math. So what do we have here? Modulo. Divide. Adding, subtracting. Okay. 643, 71, 76. So we have 6, 3, 1, and 6. So that doesn't work. Divide 0, 4, 7. That doesn't work. All right, so 6 plus 0, 3 plus 4. And wrapping this around, that should give us a 3. So it looks like adding works. How many times was used? Not temporal locality. Worst fit. Go into our biggest bucket. And your math again. Let's see what 6, 2, 3, 4. All right, so modulo. What terminates a failed linear probe? All right, so it's a full hash table. All right, so we got our table 10, 20, 41, 25, 63, whatever. 11, and say we try to land here. And we see, oh, that's not good, that's not good, that's not good. And we wrap around, not good, not good. And then we start back where we started. So we're visiting the original hash index. Yes, near each other's spatial locality reference. Or duplicate. Which was number one? Or wherever that one, I guess we haven't got to the shift one yet. Okay. Let's see if hash table's arrays is resized. All right. If we change the table size, we have to rebuild the whole thing because table size, right, is part of the normalization process. I'll get back to the earlier questions in a bit. Chain hash table, maximum entries, linked lists, right? So however much memory the system will let us have is going to determine the actual limit. All right, recent, that's time, so that's not spatial. Hash function. All right, so we got division, MD5, SHA, mid-square. Those are various hash functions we talked about. Where he wants to go to 2, can't go to 2, so it goes to 3 with a linear probe, right? Yeah, linear probe. Tricolor, which set was only garbage at the end. It's the white set. Perfect hash, no collisions. So, no, no, no. All keys at that table without any collisions. Alrighty. Garbage collection. Black set, gray set, white set. All right, so A and G in the gray set. What else in the white set? A goes over. Nothing else changes. G goes over. G brings D. D leaves. Who does D have? D has C. So B, E, F, H. E, C. C going no one else. So B, F, H. We're going to be garbage. B, E, F, H, garbage. Table size, like probably collision, the function, the load factors, that's all of those. Load factor, right? It's number of occupied versus the table size. All right, so ratio, shift folding, fancy calculator out. 987 plus 412 plus 536, which is the free point. I'll do that. I'll just go add 1 point to everyone's test score. So if you got that one correct, then you got the bonus point. If you didn't get it correct, well, you get credit. Added back. All right, double hashing. It is less vulnerable linear quadratic programming. Probing, not hashing the hash value, avoids collisions. That doesn't matter. This is second index in the array. All right, so it's less vulnerable to clustering because we have jumping off in different patterns, right? Use a separate hash function to use for the offsetting amount. 40 goes to 1. Not much really changing in that question. Quasi duplicate. All right. Line 23. So, all right, we've got our table size, uninitialized, -1, formula occupied, -2. Line 23 inside our probe function. All right, so probing needs the loop. So we're gonna need a loop in here somewhere. And that'll be it right there. Switch these as a loop, 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 loop. That was a loop. Line 59. 59 over here in our destroy. All right, so let's see what destroy is being called by. Destroy is being called. No, destroy is a private function, so that one's being called by delete. Go through and destroy something when we can't find it. So if we found who we're looking for, we should at this point set the array of index equal to our dirty. All right, so the other way we do these is just look at the answers and see, does this fit? Return the modulo. No, that's our hash function. An if statement, we're already inside our if statement. Return false, well, return true right after that. Another if statement, not so much. Return client itself, no, not recursive, not defining the table. Should be a while loop. Assigning it's being dirty, that definitely fits. This one doesn't work because there's no I in context. So, all right, process of elimination, getting stuck and figuring out what the code is supposed to be doing. Should help get you there. Line 105, 105. Yeah, which earlier was calling destroy. Doesn't have, okay, so submit button. Oh, I mean 27, 28. I forget to click buttons here. Oh, I was just skipping past them. All right, which one was 59 again? 59. Guess my clicking didn't quite work there. 66. 66. All right, final statement. It says returns a bool. So it's going to return true or false. And true is not an option, so it should be return false. We were unable to destroy something because it wasn't there to be destroyed. All right, try the submit button again. There we go. I made a goof somewhere. All right, so number 6. Get our numbers back out again. Should have saved it. All right, so modulo plus divide and modulo minus divide. All right, so our modulo is just the last digit. Divide would be the first digit. All right, so it can't be modulo because there's a collision. So we're not gonna have a perfect hash. Can't be a divide because there's a collision. We'll get a perfect hash. Now we gotta add 6 plus 0, 3 plus 4, 1 plus 7, and 13, which wraps around. And that'll be good to go, giving us perfect hash. All right, so even if you don't account for wrapping and you just look at numeric results, these hash values have no collisions. But normalization would be needed. Yeah, because 10 goes to 0, 11 goes to 1, 12 goes to 2, and 13 goes to 3. Right? Well, these are hash functions. And hash functions are not necessarily going to be in range of the table. That's where the normalization step comes in. To the question, do we want to look at again?
Professor, I'm sorry, you said that if we did which question and we got it right, we would get an extra point.
Well, everyone gets an extra point. So if you actually got the shift folding correct, that means everyone gets credit for the question. If you got the answer correct, you'll get the extra point for the shift folding. I'm guessing I didn't. No, I typed in right. Who did I miss? Line 78. Was I looking at the wrong line number there? I was definitely looking at the wrong question. Yeah, that's what I did earlier. I did 66. That's why I jumped along there. All right, click the wrong answer. Okay, any other questions about anything at this point? Right. Next week, it's just a final land. Give everyone a chance to show up, and then we will take it by the horns and do our best to knock it down. Go over number 3. All right, so typically it will exhibit data fragmentation. There's an important word here being typical as opposed to what can. No, there's no lecture after the final. Once you're done with the final, you can head off to your next final, work on late work. We have until the end of the semester, so let's go grab syllabus. Calendar. Last day of the semester, I think was it Wednesday or Thursday? We are in the 23-24. Year's almost done. All right, so got till the 20th. Well, all right, we'll just do the. No, that's all right. So late work, good till the 20th. All right. Remember the floor value for late work is still 25%. Even if it's the very first lab or the very first program assignment, you can still turn in by the 20th and get some points. You can certainly cause internal fragmentation within the linked list itself. It all depends on what the data field is, but usually the data field is just going to be a reference to whatever object type is. Right, because the list is going to be well, templated type thing in here where you'll have T data and you'll have list T star next. Is it enough to go over all the tests for the final? That'll probably get you 80% of the way there. I mean, my first thing, go retake all the practice tests, go relook at all the questions on the old tests. That's the first place I would start studying. Then from there, the labs. I wouldn't bother going over the programming assignments so much. Those are too heavy for the test. The labs are good because we can definitely see code like we would see in labs, just like we did on this test and the other tests. All right, and then the book for anything that feels unclear to help reinforce things. Yeah, so a multi-answer grading mechanism. Wrong answers offset right answers. Try to, when I use multi-answer questions, I'll try to typically bend the questions such that they're more, or because if I like negate it, right? So there's eight answers, there's 3 right, 5 wrong, but I could negate the question, that makes it 5 right and 3 wrong. Try to do it that way. That way the partial credit grading mechanism works in your favor. Yeah, that's how Canvas does the partial credit.
Professor. What would you recommend? I know you kind of talked about it, but what would you recommend to study for the final, like the most important topics?
It depends on each person. Most important topic to you would be the one that areas you understand the least, but I would do that as a second pass. First pass, right? Binary search, linear search, those are simple. You should make sure you got them in the right bucket. Don't confuse binary search versus the binary search tree, right? Those are two different topics. All right, so make sure you've got a good, everything is ringing bells, and then I would check anything that isn't ringing bells just by looking at it quickly, and then those I would spend the extra time on. Because spending extra time on a binary search or binary search tree, then you have your marginal gains will be lesser because you'll probably get the answer right versus not remembering how to do Dexter's first single point shortest path type thing and not being able to recognize it at all because it's going to be very hard to guess at that one, right? The ones where the algorithms, make sure you understand the algorithm because if you understand the algorithm, then you can work through the problem.
Okay, so binary search and you said linear search?
No, it's not what I was saying.
Oh, sorry.
I'm saying whatever is not the clearest is the stuff to spend extra time on.
Okay.